This is the narrated PowerPoint for Lecture 3, Section 2. The topic is calibration. More specifically, I will introduce a couple of concepts related to adjusting instruments and a procedure that I want you to use for calculating linear calibration curves using a least squares based procedure. One purpose of calibration is to find the relation between a physical change a sensor or transducer senses and the instrument or sensor output. Another purpose is to check an instrument system to confirm its accuracy. If the system is outside the desired accuracy tolerance, someone needs to adjust either or both the unit's sensitivity or zero offset to bring the instrument's response back into spec sheet specifications. For this class we will focus on the first purpose, finding the relation between a sensed physical change and the instrument's output. Every sensor needs to be calibrated to find the relationship between the sensor output and the sensed physical change. For example, thermocouples with dissimilar metal junctions generate a small electromotive force or voltage in response to the temperature sensed. A calibration curve is needed to relate the electromotive force, or EMF, to temperature. The relations for thermocouples are nonlinear. In lab this week, you will use a single-term potentiometer and the PDAC-55 connected to a computer to measure voltage as a function of the potentiometer position. We could have you calibrate the potentiometer to measure position by recording voltage. We will use other sensors in lab where some physical change causes the sensor to generate an output that we can measure. And sometimes I will want you to find the relationship or calibration curve. Calibration curves come in different forms. They can be linear, quadratic, a power function, or a nonlinear relation. For this class, we will work with linear calibration curves. Here is a graph with a linear calibration line that has been found to best fit the data plotted on the graph. Note that this looks similar to the sensitivity graph. The equation of the best fit line is given by y, which is the output, equals a times x, which is the input, plus b. Also note the input span and the output range. The device should always be used over the calibrated input span and output range. Going beyond those points is extrapolation, which may not give results within the device's specified accuracy. Many electronic instruments use a linear relation between the sensed input and the instrument output, and these instruments commonly have two kinds of adjustments. One adjustment adjusts the slope of the calibration curve, which is the sensitivity of the device. The second adjustment is the zero offset. The zero offset keeps the slope constant but moves the entire calibration curve up or down. So when adjusting instruments for calibration against known inputs, you can usually adjust the sensitivity and the zero offset. The sensitivity adjustment changes the slope, which corresponds to changing a in the linear relation y equals a times x plus b. The zero offset adjusts the whole line up or down and corresponds to changing b. At several points in this class, you'll be asked to develop a linear calibration curve for some data you collect in the lab. You are to use this linear regression calibration procedure. The linear relation that you will develop from the data is in the form of y equals a times x plus b, where y is the device output in response to a known input x is the actual or known inputted value, a is the slope and sensitivity of the calibration line, and b is the offset. And we will have a procedure for finding an uncertainty value using the error mean square s of y squared and three standard deviations s of a, s of b, and s of x. Let's go through the example in the course packet. The example uses a deadweight tester to calibrate a pressure gauge. You will use a deadweight tester in a lab later in the semester. Deadweight testers are devices that can create known pressures very accurately. They are commonly used to calibrate pressure transducers. For our example, we will assume that we are using the deadweight tester to calibrate an electronic pressure sensor. The sensor has a digital output that gives a millivolt reading. What we want at the end of our calibration procedure is a relation that gives us the pressure in kilopascals given the pressure transducer millivolt reading. We will write the final calibrated expression as x equals alpha times y plus beta. Note that the equation wanted at the end is different than in the previous slide and the next slide. We start with the expression y equals a times x plus b. where X is the actual pressure input generated by the deadweight tester, and Y is the millivolt output from the transducer. We need to find A and B and some statistical terms so that we can find the uncertainty of the calibration curve. This example is in the course packet beginning on page 3-7. There are 22 data readings from 0 pressure up to 10 kilopascal pressure. One set of data, 11 values, was collected by adding weight to the deadweight tester. The other set of 11 values was collected by removing weights on the deadweight tester. This was done to see if we could detect a hysteresis effect on the sensor. We will talk more about hysteresis later in the course. The notes give the intermediate values needed to do the calculations. They are summarized on page 3-7 and 3-8 and shown here. What we find is that A equals 1.08 millivolts per kilopascal and B equals minus 0.85 millivolts. So we get the expression Y equals 1.08 times X minus 0.85. But we're not done yet. This expression gives us the millivolt result Y given the known deadweight tester pressure X. When we use the pressure transducer later to measure unknown pressures, we want to have X equals alpha times Y plus beta. We want an equation that will take the transducer millivolt output and convert it to a pressure that the transducer is sensing. So we need to reorganize the equation using algebra. We add 0.85 to both sides and divide both sides by 1.08. After doing this, we find that alpha equals 0.926 and beta equals 0.787. So the calibration equation we will use with the sensor is X equals 0.926 times Y plus 0.787. The last thing we want to find is the uncertainty associated with the transducer output. We will assume that the errors are small and have a normal bell-shaped Gaussian distribution, and that the 99.7% uncertainty is given by plus or minus 3 times S of X. The equation for S of X is given on page 3-8 of the notes. S of X equals S of Y divided by A. The equation for S of Y squared is given on page 3-6. For this example, Sy squared equals 0.0433 millivolts and A equals 1.08. So S of X squared equals 0.03712. So S of X equals 0.19. And the 99.7% uncertainty is 3 times S of X, or 0.19 in this case. So 3 times 0.19 is equal to plus or minus 0.57. So if the millivolt value is 4.32 millivolts, the pressure is 4.32 times 0.926 plus 0.787, which equals 4.79 kilopascals. The result with the 99.7% uncertainty is 4.79 plus or minus 0.57 kilopascals. This is the end of the presentation on calibration for Lecture 3, Section 2. And this is the last video for Lecture 3, which covers uncertainty analysis and calibration. Again, please write down questions that you have after watching this video and bring them to class or lab.